Welcome, everyone, to the February RISE Hub seminar. I'm delighted to present our speaker today, Dr. Carmen Menoni, who is a distinguished professor at Colorado State University. She is also the director of the IFE STAR RISE Hub. Dr. Menoni was also the recent recipient of the 2026 Maria Goeppert Meyer Award in Photonics from SPIE. With that, please take it away, Carmen.
Thank you, Jimmy, and thank you all for participating. I am delighted to give this seminar to students from the RISE Hub who actually make very important contributions in research too. So I am going to talk about coatings, which is optical coatings, which is the area, one of the areas of research in my group. I am a person who loves materials, as you will see as I go through this seminar, and in particular, I am working now on oxides, but I was not trained on oxides when I was a graduate student. When I was a graduate student, I did work on very different than what I am doing that now. I basically studied phase transitions under high pressure on silicon and germanium. From there, I evolved to working on semiconductors, and now from semiconductors, I evolved to working on oxides. So laser technologies have played a pivotal role in science, and these are three examples that were essentially their contributions are so important that those who led this work received the Nobel Prize. So in 2017, the Nobel Prize was awarded to Rainier Weiss, Barry Baric, and Kip Thorne for precision interferometry for the detection of gravitational waves. And as you see here, a gravitational wave detector is an interferometer, and I am going to show you how we are contributing to making these interferometers even more sensitive. In 2018, Donna Strickland and Gerard Moreau received the Nobel Prize for methods for generating high-intensity pulses. And this is the method that we use to build lasers like the Aleph laser. In 2023, Pierre Agostini, Anne Lullier, and Ferenc Krauss received the Nobel Prize for experimental methods to generate attosecond pulses of light for the study of electron dynamics in matter. And again, this concept relied on the concept of shear pulse amplification, because the shortest possible pulses, we obtain them using shear pulse amplification drivers in combination with high harmonic generation. Another example of the impact that lasers have played in technology is extreme ultraviolet lithography, because extreme ultraviolet lithography essentially uses a laser-created plasma in a tin, from a tin source. Here we have droplets of tin that are hit at a repetition rate of 50,000 hertz every time, I'm producing a plasma that then produces the EUV light at 13.5 nanometers that we use to print the most advanced semiconductor chips. This is the picture of the stepper, and this is how the light is guided into the mask and focused to print the chips. And using, as you see here, over the years, the rule of the game in lithography has been to reduce the wavelength of the illumination, because the smallest dimensions that we can print depend on the wavelength of the illumination. So here we have this equation, Ki lambda over Na. Na is the numerical aperture of the optics here, of these lenses, and Ki is a quantity, is not a constant. I mean, that is a quantity that the lithography industry also uses to reduce critical dimensions. And of course, we know that all of these small patterns have really a big impact. And another important application of lasers, which has received lot of visibility since 2022, is inertial fusion. And this is the area where we are all working now, trying to develop laser optical technologies and optical diagnostics and understanding the fundamental science of laser fusion. That's what we do within the RISE Hub. And the impetus on fusion essentially is the result of many years of research at the Lawrence Livermore National Ignition Facility, which resulted in 2022 in essentially a breakthrough, because it was demonstrated that the energy that was delivered from the laser actually resulted in fusion energy, and that's measured by the energy of the number of neutrons that are generated in the reaction, that was greater than the laser energy that's what put in, and that's what we call ignition. Since this initial demonstration, there have been many other experiments, and in fact, I don't have all the right data. I mean, in April 2024, they demonstrated a 4x gain, but now in 2025, they demonstrated an 8x gain. So in the concept that Livermore uses, there are 196 beams that are impinging on this capsule that is called the Hull Room. These are UV, ultraviolet laser beams of nanosecond pulse duration. And approximately of the energy that these beams carry, approximately 230 kilojoules of energy are estimated to be absorbed in the Hull Room. Now, in this type of fusion concept that is called an indirect drive, the UV laser light is absorbed by this metal capsule, and in this process, X-rays are generated, and these X-rays are the ones that cause the implosion. So this is the reason why we call this indirect drive. And in this implosion, the fuel, which is inside this capsule, is compressed to hundreds of thousands of degrees Kelvin and gigabars of pressure to fuse the deuterium and tritium that is the fuel material. So based on the demanding needs from science and from technology, in 2023, the Department of Energy and the NSF organized a basic research need workshop on laser technologies. And these workshops are frequently organized by the Department of Energy because they guide the direction of research for the next 10 years. And in this workshop identified 4 research priorities to advance ultrafast lasers and the science that they enable. And I show here all the different areas that we discussed, but I am only going to concentrate on this area because in order to advance ultrafast lasers operating in the spectral range from the UV all the way to the infrared, we need to reinvent materials and optics. So this is what I am going to cover in this seminar. And what you see here is essentially all of the components that come into play in making an ultra high intensity laser. TIP is a solid state laser, so we need diodes to pump the gain media. We need coatings to essentially coat some of these, for example, the facets of the amplifiers with anti-reflection coatings. We need mirrors to guide the beams, and we need gratings. Gratings because all of these lasers use this concept of shear pulse amplification. So we are typically generating high energy beams that have of long pulse duration, and in the last stage, we are going to compress the pulses. And so notice here are coatings, and coatings essentially are needed to achieve high intensity. This is, for example, the left laser fits here. To achieve high average power, these are short pulses, picosecond, lasers that produce in terawatt peak power that operates in the kilohertz, ytterbium YAG, and other lasers fit here. Few cycles, these are essentially the lasers that produce attosecond type of pulses. And of course, high repetition rate are the operating in different wavelength range are used for chemical sensing and spectroscopy, for example. So coatings, are made. I will show you how they are made, but they are essentially electromagnetic devices, passive electromagnetic and photonics devices. Why do I say that? It's because a coating, like for example, a high reflector coating, like I show in here, consists of a stack of two materials that have contrasting refractive index at the laser wavelength. So for example, here I show a stack of a material that right here is, you would read it as hafnium oxide, and that is the high refractive index material. The low refractive index material is silicon dioxide. Now, these materials are amorphous, and these are the type of materials that we grow in the lab. Because they are amorphous, I will call them hafnia and silica. Now, depending on how the layer thickness and the refractive index, I can use programs to design the optical response. And so, for example, I show here how in this particular case, if we use quarter wave optical thickness, then I will design a mirror that in which the reflectance looks like this. This one was designed for a center wavelength of 1030 nanometers. So we can now typically grow hafnia silica coatings at 1030 nanometers with, for example, 30 parts per million absorption loss without annealing. The challenge is that when we grow these coatings, they will have high stress, which is 400 megapascals. And their laser damage fluence is of the order of 20 joules per square centimeter at 280 picoseconds. But when we go to 40 femtoseconds, then the laser damage fluence decreases significantly. So for high intensity lasers, the coatings that we develop have to have the highest possible laser damage performance. And if we go to very short pulses, we also have to take into consideration that the bandwidth of the mirror, for example, has to be sufficiently large to propagate this 40 femtosecond pulse. Now, in interference coatings for gravitational wave detectors, the rule of the games are completely different. Again, we use multilayers of two materials that will have contrasting refractive index, but now the materials that we use are different. And I am going to show you in the next slides why they are different. Specifically, in gravitational wave detectors, and this is a picture of the mirror that is in the LIGO detector, either at Hartford, Washington, or Livingston, Louisiana, the two detectors that are here in the United States. You see the mirror is a 40-kilogram fused silica substrate that is amazing. I mean, it has a very stringent figure of error and extremely low absorption in all this bulk. And then it's coated with high reflector coatings that now are a combination of silica and a mixture of titanium top tantalum. So the challenge in these coatings is that in the high index material, mainly, we have motion of the atoms that is a thermally activated off-resonant motion that causes elastic energy loss. And the way to think about it, I mean, the interferometer can measure displacements of an atometer. This is a 4-kilometer long interferometer. If I have a motion of the atoms, even at atomic length scales, the atoms behave like atomic drums, and so the signal that is reflected will have noise, and this noise shadows the noise from the gravitational waves. So the rule of the game here in these coatings is to reduce coating thermal noise. We grow our films using a technique that is called ion beam sputtering. And I show here a schematic of the ion beam sputtering system that we have downstairs here at the ERC, and that some of you are using. So in this system, we have a main ion source. This ion source produces a beam of ions, typically argon ions, that sputter a metal target, and they dislodge atoms and molecules from the target, producing a plume that then deposits onto the substrate. And the substrate is typically rotating for uniformity purposes. We do all of this in an oxygen-rich atmosphere because we want to make oxides. And we control the temperature of the substrate. What this process has is that it produces coatings that are very dense. They almost have the density of the crystalline material, and thus they are environmentally robust. Using this system, we can grow binary oxides such as hafnia, tantala, germania, scandia, and so on. But we can also make mixtures. And the ability to make mixtures is very important for the coatings for LIGO. I show you here pictures of a transmission electron micrographs of a multi-layer of silica hafnia. And what you can see here is that we have the interfaces between the two materials are very sharp. And we need that to tailor, to have a good contrast and tailor the optical response. We can also make other type of materials that are called nanolaminates. And here what we do is we grow very thin layers. This is 5 nanometers. Here this bar was 1 micron. So notice that these layers, the thickness of these layers are less of the order of 2 nanometers or 3 nanometers, and this one is thicker. And then we stack them. And then we use these layers to replace, for example, the high index layer, hafnia layer in a coating. Now, when you look at these materials using typically any technique, like for example, transmittance measurements, and the materials are, number one, transparent over a very broad range. And this is the reason why they are so prevalent in designing coatings for lasers that operate from about 200 nanometers all the way to 2.3 nanometers. Then water absorption starts to be a problem. They are very uniform. They can be deposited very uniformly, and I show here that the absorption loss is very low, and over over the film, over the substrate area. If we look at it, if we take it to an X-ray machine, then what we will know is that these materials look amorphous. I show here where the peaks, for example, for tantalite of the crystalline material should be, and you see very broad peaks. This tells me that are amorphous. And the TEM picture shows me that there are no inclusions or nodules when you grow by ion beam sputtering. However, the process that we use to grow these materials is physical vapor deposition, and this is a low temperature process. So this cartoon here shows that when the molecules and the atoms are dislodged from the target, they fall into the substrate, which is typically at a temperature of about 100 degrees C. They stick to the place where they land and have very limited mobility. So as a result of this, then it is very difficult to control the network organization in these materials. And the way to think about it is that these are tetric materials, and you see here a tetric picture in which now these are the atoms and molecules that land, and they are very disorganized, and therefore they will give you a material in which is poorly packed. But we can control, if we can control that, then we could get a network that is more densely packed. And this densely packed network is characteristics of what are called stable glasses. Stable glasses are grown by nature by cooling the liquid from very, 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 very slowly. So we are growing essentially these materials in the lab. So the way to think about it now, I'm showing you here two curves of how I can make an amorphous material. This is when I make it from the melt. So I have liquid here, and then I start cooling, and I go through the liquid to solid transition, and that is characterized by a temperature that is called the glass transition temperature. And so here now I have a solid. But notice that if I go much slower, now I will be able to get a very different configuration in the amorphous material than I do when I cool very fast. And typically, I show you the example of amorphous germania at the atomic level, and in what we call the short range, in the range of about 5 angstrom. In germania, the germanium atom is coordinated or is connected to 4 oxygen atoms, and these are how essentially the molecules connect. And when you cool very fast, and you again, we will obtain an amorphous material, but it will be characterized by very small rings. And if we instead cool very slowly, then we will obtain large ring sizes. And this is a characteristics of a stable glass. In germania, I am going to show you that we typically observe 3-member rings and 6-member rings. So we ask ourselves whether it would be possible to deposit a material by ion beam sputtering that would have a network organization of glasses, and more important, of stable glasses. And there have been predictions, model predictions, that claim that we can do that if we grow the material at temperatures that approach the glass transition temperature. So we did some search among all the families of oxides, and we realized that amorphous germania has a glass transition temperature of about 78 Kelvin, which is very accessible with with the deposition system. We can heat up the substrate to temperatures. I mean, we did heat up to about 400 C. And so then we said, okay, we're going to deposit the material. And then the next thing is, in order to look for signs of structural stability, we need to be able to detect large rings. And so to do that, we conducted Raman spectroscopy measurements of amorphous germania that we deposited by ion beam sputtering using essentially room temperature for the deposition. And then also we did a separate deposition at a substrate temperature of about 0.8 the glass transition temperature. And the Raman spectrum of germanium has contributions from mainly from 6-member rings. This is the red spectrum, and 3-member rings. And this is the green line here. So the black is what we measured in Raman. Then what we found is that if we go and we deposit at higher temperature, you see that the intensity of the red peak increases compared to the intensity of the green peak. And that indicates that indeed the material has now a larger proportion of large rings. So here I am plotting the normalized area A6. This is the area of the 6-member rings as a function of the substrate temperature. These are the green diamonds, and purple squares, and also as a function of annealing. And what you see here is that the predictions of the model agree with the experiment, because when we grow near the glass transition temperature, we actually obtain a more stable glass-like material. And then when we grow at room temperature. In addition, annealing also alters the network organization in amorphous germania, but you can see again that the annealing is more effective whenever we start with a better organized glass. So this was the very first time that we demonstrated that this effect has been observed in an inorganic material. All of the previous studies and even the models were essentially developed for organic materials, because it's very easy to get to the glass transition temperature in an organic material. So then we plotted the area of the 6-member rings, and we took that as the parameter. This indicates higher organization, higher network organization, and we measure internal friction in the coatings, and we saw that there is a reduction in the internal friction. And this is what we need to make good coatings for gravitational wave detectors. In fact, we measure an internal friction, which is the second lowest compared to silicon among all of the oxides. In addition, we collaborate with a group at Northeastern University that is doing modeling of the oxides. And what the models showed is that when we have a larger proportion of 6-member rings, all of these rings are connected. Instead, all of the smaller rings are disconnected. There are other studies that have been conducted in mixed oxides with the goal to try to understand how we can make better alloys for gravitational wave detectors. And what I show here is work that was conducted by our colleagues at Stanford that showed that when we anneal materials, essentially this is grazing incident pair distribution function measurements. These are done at the synchrotron. And what I show here is that the way that these polyhedra here are polyhedra, not tetrahedra. Like this is, imagine tantalum connected to tantalum atom connected to oxygen. The way that they connect is important. And so this shows that when we favor phase sharing connections, as it happens with annealing, then the internal friction is also going to decrease. We have done a lot of work on alloys. On these alloys, we have shown that alloying also has the benefit of increasing crystallization temperature. We have demonstrated that in Germania, there is cation diffusion. And again, this is important because it allows the atoms to rearrange and form a more favorable network. And we also look at stress in the coatings because ultimately we are going to make multi-layer dielectric coatings. Now, in Germania, we demonstrated that yes, it has these extremely low mechanical loss, but there is a challenge. Germania has a refractive index of 1.6 at 1 micron, and silica has a refractive index of 1.45. So therefore, we needed to increase the index to be able to use it in a mirror. And because of that, we started to add titanium. And we stopped at a composition of about 0.44, which was in a sense serendipitous because we didn't know that that alloy was going to give us the lowest mechanical loss. Nevertheless, we have done also studies in the material. We looked at the Raman spectrum. In collaboration with our colleagues at Northeastern, we showed that indeed this particular composition is very special because we can form a network like I'm showing here, in which you see we have the majority are Germania or titania bonds, and these are forming a network in which all of these molecules are connected by sharing corners. And this is what we need to have low internal friction. And so when we anneal this material, we can actually get an internal friction that is just as low as Germania. And this value of internal friction is such that is about a 3x reduction with respect to titania tantalum. So next LIGO coatings call for a reduction of approximately 4 in the internal friction, and which results in approximately a reduction of 2 in the coating Brownian thermal noise. So what we are doing right now, and we have been doing for over the last 2 years, is we are developing coatings. The best that we have obtained is 0.6 A LIGO. These are the present coatings in thermal noise. And we have obtained absorption loss typically in our chamber is of the order of 1 to 2 parts per million at 1064 nanometers, but we have transferred the recipe to LMA, a company in France that is going to coat the test masses. And in their chamber, they can actually reach half a part per million at 1064. So what will these coatings make possible? Well, these coatings will make possible will expand the reach of gravitational wave detectors because they will be able to detect events that occur very close to the time in which the universe was formed. And in addition, they will increase the rate of detections. So what is what we have learned from all this work? And how can we apply it to high-intensity lasers? So we learned that the network organization in the materials is important. And we can actually improve network organization if we make alloys. Alloys in which we will have 2 cations and then oxygen. And also, we have models now that can predict the structural properties of these physical vapor amorphous oxides. So we are to design coatings for ultra high intensity laser. And I show here an example of the two lasers that we have at CSU. We have a high repetition rate joule laser that produces joule level pulses. And then we have the Aleph laser that produces petawatt peak intensities at rep rates of up to 3 hertz. So the parameter space is very different. So as a result of that, what we need to do is we need to actually look for strategies that include looking at new materials, looking at stress control, understanding the role of interfaces, controlling dispersion. This is especially necessary for the Aleph laser. And also substrate conditioning. And all of these comes into play in designing coatings for these lasers. And the typical materials that we use right now are hafnia silica, and we can make coatings that will have a very low absorption loss at 10, 30 nanometers. But it turns out that absorption loss, when you have picoseconds or femtoseconds, is not the dominant parameter. It is a dominant parameter when we have nanosecond pulse duration. We collaborate with a group of Inan Chowdhury who is doing modeling on these coatings. So the rule of the game on coatings for high peak and average power, near infrared, even to UV lasers, is to increase the laser damage threshold. And what I show here, this is a picture from the report that we wrote in the DOE BRN, is that the laser damage threshold is dependent on pulse duration and on wavelength. So notice, this is femtosecond range, this is nanosecond range. I go from values that are extremely high, 60 joules per square centimeter, at a wavelength of about 400 nanometers. If I come here, there are no results, but the laser damage will be of the order of maybe 0.5 joules per square centimeter. So this is the challenge. And so you may ask, what is causing damage in these materials? And there are lots of models that have been developed to understand damage in these oxide materials. And essentially, we have the dominant processes that cause damage are electronic processes that occur because we have single and multi-photon absorption, we have avalanche and impact ionization process. And the way to think about it is that when we focus a very high intensity beam onto the coatings, these linear and nonlinear processes essentially are going to promote electrons from the valence band to the conduction band and are going to create a sufficiently high electron density that resembles that of in a plasma. And that is like having a little electron gas ball in the material that starts to create instabilities in the bonds and starts to create and break bonds. And that essentially is the onset of damage. So in the coatings, we actually selecting the materials with the largest band gaps is very important because we reduce multi-photon ionization processes. So we typically use hafnia and silica. And most of the coatings here are hafnia silica. And then we also play with the standing wave electric field intensity within the coating. These are some examples of work that we have done with our colleagues at Ohio State. And what I show here is I show you essentially the laser damage behavior of a hafnia silica mirror for pulse durations of less than 100 femtoseconds. So red is 260 femtoseconds, green is 25 femtoseconds. And essentially what you see is that as I go shorter pulse, then the laser damage threshold decreases. Further, the laser damage threshold decreases when I increase the number of pulses that I hit at a given site on the coating. The way to think about it is, okay, now I have high repetition rate in this case. So dependent on pulse duration is dependent on repetition rate. And what we also showed with our colleagues at Northeastern is that actually the onset of damage occurs via the lamination in the layer where the critical electron density is the largest. And that's what these plots here show. Also with Ohio State, we have done studies on gratings. Gratings are very critical components in high peak power lasers that show how, for example, cracks, particle nodules affect the laser damage behavior of the gratings. And what you see here are essentially simulations that show the electric field distribution within the grating. And you see that in the pillar where we have these steps, we have very high electric fields. And of course, that is going to be it's going to be essentially a source of, a precursor to damage. Now, what are we doing, for example, to help advance the upgrade of the Aleph laser? This is the architecture of the Aleph laser. This is a titanium sapphire laser, and that is pumped by frequency double green light from a neodymium glass amplifiers. And what you see here is that the laser beam after is essentially amplified, it goes into a compressor, and then from the compressor it goes into two stages where you do into two chambers where you do experiments. And at a certain point it is frequency double, but nevertheless, one critical component of this laser is the compressor. So we are trying to look, number one, on working on coatings that will have higher damage threshold at ultra short pulse duration and gratings, dielectric gratings that will have also very high damage threshold. We're also playing some other games with the Aleph laser. And what I show here, this is work that we did recently. Some of the challenges when you have high intensity lasers is that you cannot use regular optical elements. So the way to make a circularly polarized beam out of a linearly polarized beam is to use a wave plate. But the wave plates are not good for whenever you have to propagate. In this case, we are propagating joule level pulses of about 40 femtosecond duration. So what we did is we made a mirror that actually can phase shift the S and P components of the incoming light, and so we come in with a linearly polarized light, and this is the mirror that we made. And here, out of this mirror, we have elliptically polarized light, and then we design the coating such that after the light bounces over these two mirrors and goes into the chamber, we will end up here with circularly polarized light. And it was used in an experiment in which electrons were actually being steered by the circularly polarized light. We obtain an ellipticity of approximately 0.0361, which is very good. It's telling us that we make circularly polarized light. So the idea here is, okay, if we cannot use optical element, let's use mirrors to play all these tricks and be able to propagate very high intensity laser beams. Now let me move to fusion and what we are doing, and I will use this platform to show you the work that we are doing in coatings for the three laser fusion platforms that RISE is supporting to develop with different technologies and with fundamental science. So these three different driver. I mean, we have three companies participating in the Rice Hub. Excimer Energy is developing excimer lasers that will generate tens of megajoules ultraviolet beams that will essentially hit the target, the capsule in the target. Now, in this approach, the only needs optics here on the beam detectors, and so we need to essentially direct the beams into gas cells because the pulse compression and the pulse beam combining is going to be done using nonlinear optics. So this is the concept that Excimer Energy is using. The concept of that blue laser fusion is proposing for its driver is essentially a cavity that is like the LIGO cavity, is an optical enhancement cavity. And so you need mirrors that will have 5.9 reflectivities and will have extremely low absorption loss and very high laser damage threshold. And the approach that Marble Fusion is using, Marble Fusion is developing high peak power lasers of essentially petawatt lasers, and there will be many of these lasers impinging on a capsule, and these essentially, these concepts exploit the ability to generate very efficiently hot ions, hot electrons, and radiation when these ultra high intensity pulses strike targets that are nanostructured targets. The blue laser fusion and Excimer Energy will use foam targets that I show here. Now, the NIF laser operates at 355 nanometers. So we have been doing some work also for coatings for 355 nanometers. And what we showed is that, again, going with mixtures allows us to actually achieve laser damage thresholds in anti-reflection coatings that are very challenging because they are the lowest laser damage threshold component that are very similar, are very high, of the order of 6 joules per square centimeter. Here, the pulse duration is of the order of 10 nanoseconds. In support of the Excimer Energy approach, we are making that the coatings will go into the amplifier, and on the windows, there will be some coatings on the windows of the Raman cell and the Brillouin cell, at least at the entrance window. And so we have been looking at hafnia silica coatings, and we have done some studies to understand what is the laser damage behavior and the fatigue behavior that the coatings show whenever we have multiple pulses. So this simulates high repetition rate. And in support of the blue laser fusion concept, essentially we are using the design of the coatings that we have for LIGO. And now what we are trying to do is modify the materials to essentially achieve a higher laser damage threshold. And these are some of the coatings that we developed for 1064 nanometers, and they were designed on hafnia silica, and we obtained a very, very high transmittance, 3 parts per million, and an absorption loss that is very low, of the order of 1 parts per million. We're also working in collaboration with Texas A&M, they are also members of the hub, in trying to develop ways to be able to predict the multi-pulse degradation that coatings experience in fusion laser drivers. And so our colleagues at Texas Tech developed a model that is based on extreme events statistics that essentially requires inputs of the laser damage behavior, what we call the single pulse laser damage behavior, and then the output will be, okay, what happens to the coatings when instead of having just one pulse incident on site, we'll have multiple pulses. So this is a paper that has just been accepted in Optics Express. So this is my last slide, and I hope oh yeah, I'm very good with time. Is essentially what you see, what I have walked you through is the process that we are using to optimize materials for coatings for very specific applications. And the materials issues are very different depending whether we are developing the coatings for gravitational wave detectors that for ultra high intensity laser. There's a lot to do. And so those of you who are working in my group, I mean, I hope this motivates you to start thinking of new ideas and so on. Especially, I mean, that we need to think out of the box on how to grow these materials, because we need to go make better glasses, and yet we are not doing that with some of the materials. We can do it with Germania titania, but not with some other ones. So we are exploring doping and mixing, we are exploring the position at elevated temperature and so on. But in addition, this result of how the laser damage starts in a coating points to the fact that we need to understand what happens at the interfaces. And we need to engineer the interfaces so that then we can prevent the film from delaminating. And also, one aspect that has not been explored in these coatings is thermal transport. And so we need to understand thermal transport. So this is it. This is my thank you slide to all of the members of my group and my collaborators, and I will be happy to take any questions you may have.
Wonderful presentation, Carmen. I actually had a question about workforce development. So, as optical coatings appear to be at a specialized intersection between material science and laser physics, I'm thinking as we scale up, projects like IFE STAR, where do you see the biggest skills gap for incoming researchers, and how can universities better prepare students for this niche field?
Well, whenever I hire undergraduate students, I essentially start teaching them skills that will, again, will prepare them to learn, to understand these materials and to make coatings and so on, and to essentially they participate in research solving real problems. So I think that this is a start, because as graduate students and undergraduate students, when you prepare them with certain skills, they are the best venues for transitioning technology. They are the ones that are going to take the new ideas to other places. And essentially, this has been figured out, for example, by companies that make software like SolidWorks, correct? That's the reason why they give it to you for free, because they know that whatever you train a student on, then that will be propagated. So that's exactly what we are doing, what I do in my research, and why it is very important for undergraduates to start working early on research projects.
Perfect. We do have a question from Richard. He said, sorry if I missed it. What is the current fluence on the NIF laser on the last mirror, and what is the LIDT for those optics?
Okay. Oh, you didn't miss it. I didn't say it. So the mirrors, I don't have a picture in this presentation. I don't think I have a picture of the driver, of the NIF driver. No, I didn't put it in. All of the optics at NIF is designed for essentially a laser damage threshold of approximately is less than 10 joules per square centimeter. Now, the main challenge on the last mirror, and I don't have it. I don't have the the architecture. Let me see if I have it in another slide set. Okay, let me see if I have it in another presentation. I think I have it here. No, okay, not in there. Okay, the challenge on the coatings at NIF is that the last mirror, that is before an optics assembly that contains the frequency doubling and the frequency tripling crystals to go from 1 omega, which is 1053, to 3 omega, that is about 351, is that there is when essentially you have these very high intensity beams that are focused onto the capsule. And I have the capsule. So we have all of these very high intensity beams focusing on the capsule. There is back propagating, there is UV light that causes some nonlinear processes. And so the main damage on that mirror comes from this back propagating or reflecting UV light. So it's not the 1 omega that damages the mirrors. The mirrors are always operated at laser damage, at almost at the threshold level.
Can I just ask one more follow-up? How many shots, like what's the average lifetime in shots of those mirrors?
I don't know, but okay. Okay. So NIF is a single shot laser, put it this way, correct? Because they do one shot and then they have to wait. A long, days to go clean up to clear up the chamber and so on and so forth. The mirrors damage, and I don't know the frequency of the damage, but just to give you an idea, they spend $40 million a year fixing the damage in the optics. They have a whole division that does that, and they have different processes that they have developed to repair the optics. The optics at NIF are just to give, are approximately 70 centimeters by 40 or 50, by 40 centimeters. They're huge. So, and their beams are huge. So as a result, because the beams are huge because they have to keep the fluence down. And so as a result of that, if they see an incipient damage on any of the optics, they can repair that. And they have a way to do it.
Thank you.
Awesome. As we approach the top of the hour, are there any more questions for Carmen?
What about a question from a student?
We have a question from George. What is the damage fluence you are expecting for your new coating technology in the 10 to 100 picosecond range?
In the 10 to 100 picosecond range. So I can give you at one micron. Let's set the wavelength at 1 micron, because if I go to 500 nanometers, then it will decrease by a factor of 2 or 3. But at 1 micron on a mirror, I have of the order of 20 joules per square centimeter, and on an anti-reflection coating is less. But I don't. It's about 10 joules per square centimeter. But I have to tell you that this is a good value for a single shot. It decreases with multiple shots. And that's the challenge when we are making high repetition rate lasers.
Great. Do we have one final question for Carmen?
I'd like to ask a question, but I'll yield to any student who wants to ask. Can I go ahead and ask?
I think the floor is all yours.
Yeah, well, first of all, really enjoyed your talk, Carmen. Great talk. I learned a lot. I wanted to ask about absorption of these coatings, and in particular, how that applies to LIGO. my understanding is that at least in some frequency range, the noise is limited because they can the noise floor is there because they cannot increase the power, even though laser power is available, but higher power results in coatings absorbing light and producing transverse mode instabilities in LIGO. And this is ultimately the reason why they're using squeezed light in the
Correct.
advanced
Correct.
LIGO. If
Mm-hmm.
only they could make those coatings absorb less,
Oh, we
they
will.
they had the much easier way toward
No,
higher
we,
signal to noise.
but we have, we have the state of the art coatings for LIGO. So there are plots, and again, I don't have them here. There are plots in which that show how essentially how the 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 detection range of the spiral range changes as a function of absorption loss in the coatings and mechanical loss. So for the present coatings, if we got what we need to decrease the mechanical loss by a factor of 4, and the absorption loss in the coating has to be less than half a part per million. And we are there. For the beam, as you correctly said, for the present beam size of LIGO. Now, for Cosmic Explorer, and we are already working on coatings for Cosmic Explorer, that will be the next generation detectors. The next generation detectors are not going to be 4 kilometers long, they're going to be 40 kilometers long. The intracavity power will be higher, the mode diameter will be higher. So we need to decrease the absorption loss. Their absorption loss is very important. So we will have to decrease it to 0.1 parts per million. We are already working with the LIGO collaboration on that.
Great, great. But Texas A&M has just been named #1 research university in Texas and among 25 best in the country.
Very good. Congratulations.
Wonderful. Well, thank you so much for your talk, Carmen, and thank you everyone for joining this seminar. Thank you.